Good evening, esteemed member of the class. I am Ryan Lawrence Manilhig, and I am pleased to present my report on the fascinating subject of magma. Magma is a molten or partially molten rock found beneath the Earth's surface. It is the source material for all igneous rocks. Magma is often colloquially referred to as lava. But lava is actually the extrusive equivalent of magma, meaning it is magma that has erupted into the Earth's surface. Magma is the molten or partially molten rock found beneath the Earth's surface. It's like the underground version of lava, which is what we see when magma erupts into the Earth's surface. Imagine like this: magma. Think of it as the hot liquid mixture of rock, minerals, and gases simmering in a giant underground pot. It's under immense pressure from the weight of the Earth's crust. And lava. This is the magma that has escaped from the pot, flowing out onto the Earth's surface. It's like the overflow of the underground pot, cooling and solidifying as it spills out. Magma is the source material for all igneous rocks. These are rocks formed from the cooling and solidification of magma or lava. Here a sample breakdown. Magma, underground, molten rock. Lava, above ground, molten rock or erupted magma. Igneous rock, the solid rock formed from cold magma or lava. Think of it like baking cake. The batter is like the magma and the cake like the igneous rock. Now, here are the topics for magma: rock deformation and factors affecting the kind of deformation. Our first topic is rock deformation. Rock deformation is the process by which rocks change shape or volume under stress. Is a cornerstone of earth science. It's the driving force behind many of the Earth's most dramatic features. From towering mountains to deep ocean trenches, understanding rock deformation allows us to unravel the Earth's history, understand its internal structure, and predict geological events like earthquakes. Rock deformation is how rocks change shape or size when they are put under pressure or stress. Think of it like squeezing a piece of Play-Doh. It changes shape. This process is what shapes mountains, creates valleys, and even helps cause earthquakes. Rock deformation has two parts: stress and strain. Stress. Stress refers to the force applied per unit area on a rock or any part of the Earth's crust. It's a fundamental concept that helps us understand how rocks deform and the force that shape the Earth's surface. Stress is like the pressure that a rock feels. Imagine pushing on a rock with your hand. That's applying stress. The harder you push, the more stress the rock feels. It's the force that acts on the rock, causing it to change its shape or size. Here is an example of stress. Rubbing band. The rubber band, think of the rubber band as a piece of rock. When you pull on the rubber band, you're applying stress. The more you pull, the more stress you're applying. The rubber band stretches as you pull, showing deformation. It's changing shape under stress. When you let go of the rubber band, it snaps back to its original shape. This is because the stress was removed and the rock or rubber band can recover from the deformation. This sample example helps visualize the concept of stress and how it can deform rocks, leading to the changes in the Earth's surface. So, this is the types of stress: tensional stress, compressional stress, and shear stress. First, tensional stress. So tensional stress, this stress stretches or pulls the rock, causing it to lengthen. It's like pulling the rubber band. Imagine two tectonic plates moving apart, divergent boundary, creating tensional stress. So, imagine you're holding a rubber band and pulling it apart. That's tensile stress in action. It's the force that stretches or pulls a rock, making it longer. Like the rubber band, rocks can stretch a little bit under tensile stress, but too much pulling can cause them to break or fracture. So I have an example here for tensional stress. So tension stretches rock. Here's how it applies to the earth. Divergent boundaries. When two tectonic plates move apart, they create space between them. This space is filled with magma rising from the Earth's interior. The pulling force of the plates moving apart creates tensile stress in the rocks surrounding the magma, volcanoes. As the magma rises, it pushes against the surrounding rocks, causing more tensile stress and eventually leading to volcanic eruptions. Think of like a balloon being filled with air. It stretches until it's eventually popped. So, tensile stress is like a pulling force that can make rocks longer and thinner, and it's a key factor in the formation of volcanoes and other geological features. So, the second, compressional stress. So this stress squeezes the rock, causing it to shorten. Imagine pushing the ends of the rubber band together. This is common at convergent plate boundaries where plates collide. Imagine you're holding a rubber band and pushing the ends together. That's compressional stress, a squeezing force that makes a rock shorter and thicker. It's like squeezing a punch, making it smaller and denser. So, I have an example here for compressional stress. So, compression pushes it to make it together. So here's how it works on the Earth. Convergent boundaries. When two tectonic plates collide, they push against each other, creating compressional stress. Imagine two cars crashing head on. The force of impact that compresses the metal in the cars. Mountains. Compressional stress can cause rocks to fold and buckle, creating mountains. Think of the rubber band. If you push hard enough, it would fold instead of just compressing. And earthquakes. Compressional stress can also build up in the Earth's crust, leading to earthquakes. Imagine the rubber band snapping. When you push it too hard, that's similar to how rocks can fracture and release energy in an earthquake. So, compressional stress is a squeezing force that can make rocks shorter and thicker. And it's a key factor in the formation of mountains, earthquakes, and other geological features. And the third, shear stress. This stress causes the rock to slide past itself, causing it to deform in a parallel but opposite direction. Imagine sliding the rubber band across a surface. This is often found at transform plate boundaries where plates slide horizontally past each other. So, imagine sliding a rubber band across a table. That's shear stress in action. It's a force that causes rocks to slide past each other, like two plates rubbing against each other. Think of it like the shuffling a deck of cards. The cards are sliding past each other, creating a shearing motion. So I have an example of shear stress here. Shearing can cause masses of rock to slip. And here's how it plays out in the earth. Transform boundaries. When two tectonic plates slide horizontally past each other, they create shear stress along the boundary. This stress causes the rock to deform and fracture, leading to earthquakes. Think of two cars driving next to each other. If they bump or rub against each other, it creates a shearing force and fault zones. Shear stress is the primary force that creates fault zones, which are the fractures in the Earth's crust where rocks are moved past each other. These fault zones can be miles long and are often the sites of the earthquakes. So, shear stress is a sliding force that causes rocks to deform and break, and it's a key factor in the formation of earthquakes and fault zones. Now, next is stress and deformation. So the types of stress and deformation is brittle deformation and ductile deformation. So brittle deformation. Brittle deformation is rocks under low confining pressure and high strain rate tend to fracture under stress. This is common in the Earth's upper crust. Think of a brittle glass breaking. So, imagine a piece of glass. If you hit it with a hammer, it will shatter into pieces. That's brittle deformation. It's when rocks break or fracture under stress, just like glass. Here's how it works. Low confining pressure. Rocks under low confining pressure are more likely to break. Think of the glass. It's not under much pressure, so it's easy to break. High strain rate. A high strain rate means the stress is applied quickly. A hammer hitting the glass is a high strain rate, causing it to break instantly. And upper crust. The Earth's upper crust is the under lower confining pressure than the deeper layers, making rocks more likely to deform brittly. So here are some examples of brittle deformation: faults, joints, and earthquakes. So brittle deformation is like a rock breaking under stress, and it's a key factor in the formation of earthquakes and other geological features. And next, ductile deformation. So ductile deformation, rocks under high confining pressure and low strain rate tend to bend or flow under stress. This is common in the Earth's deeper crust and mantle. Think of a metal wire bending. Imagine bending a metal wire. It doesn't break, it just bends and changes shape. That's ductile deformation. It's when rocks bend or flow under stress instead of breaking. Here's how it works. High confining pressure. Rocks under high confining pressure are more likely to deform. Ductility. The pressure keeps the rock from breaking, allowing it to bend instead. Low strain rate. A low strain rate means the stress is applied slowly. Bending a metal wire slowly allows it to deform. Ductility. If you bend it too quickly, it might break. And deeper crust and mantle. The Earth's deeper crust and mantle are under much higher confining pressure than the upper crust, making rocks more likely to deform. Ductility. Here are some examples of ductile deformation: folds, metamorphic rocks, and mountain range. So ductile deformation is like a rock bending or flowing under stress, and it's a key factor in the formation of mountains, metamorphic rocks, and other geological features. So next, this is the types of stress and earth processes: mountain building, earthquakes, volcanism, tectonics, structural geology, and geophysics. So first, mountain building. Compressional stress at convergent plane boundaries creates mountains through folding and faulting. Imagine two giant pieces of Play-Doh pushing against each other. That's simplified picture of how mountains are formed. This is called mountain building or orogenesis. So here's how it works. Convergent plate boundaries. When two tectonic plates collide, they exert a powerful compressional stress on the rocks at the boundary. This stress is like squeezing the Play-Doh together. Folding. As the rocks are squeezed, they can bend and fold, forming fold like ripples in a rag. These folds can be very large, creating mountain range. And faulting. If the pressure is too great, the rocks can break, creating faults. These faults can be very large, creating valleys and other features. Here's a quick breakdown. Folding. Rocks bend and curve under pressure. Faulting. Rocks break and shift under pressure. So mountain building is a complex process, but it's essentially a battle between the forces of compression and the resistance of the rock. The result is the creation of some of the Earth's most spectacular features. Second, earthquakes. Faults are zones of weakness where earthquakes occur due to stress buildup and sudden release. So, imagine two pieces of wood rubbing against each other. If you rub them hard enough, they'll eventually stick together. Then if you try to move them again, they'll suddenly slip apart, creating a jolt. That's a simplified picture of an earthquake. Here's how it works. Fault zones. Earthquakes occur along fault zones, which are zones of weakness in the Earth's crust where rocks have moved past each other. These fault zones are like the cracks in the wood. Stress buildup. As tectonic plates move, they exert stress on the rocks along fault zones. This stress is like the rubbing of the wood pieces. And sudden release. Eventually, the stress becomes too great and the rocks suddenly slip past each other, releasing energy in the form of seismic waves. This is like the wood pieces suddenly slipping apart, creating jolt. Here's a quick breakdown. Stress buildup. Tectonic plates push and pull on rocks along fault zones. Sudden release. Rocks suddenly slip past each other and releasing energy. Seismic waves. The energy released by the earthquake travels through the earth in the form of seismic waves. So, earthquakes are a natural part of the Earth's dynamic system. They can be very destructive, but they also play an important role in shaping the Earth's surface. Next, volcanism. So, stress can influence the movement of magma, contributing to volcanic eruption. So, imagine a giant pot of boiling water and a tube. The water is hot and under pressure and it wants to escape. That's simplified picture of volcanism. Here's how it works. Magma chambers. Magma, molten rock, is found deep beneath the Earth's surface in magma chambers. These chambers are like the pot of boiling water. Pressure buildup. Magma is under immense pressure and it wants to rise to the surface. This pressure is like the pressure in the pot of boiling water and volcanic eruptions. When the pressure becomes too great, the magma erupts through the Earth's surface, creating a volcano. This is like the water boiling over and spilling out of the pot. Here's how stress plays a role. Tectonic plate movement and fault zones. So volcanism is a powerful force that can reshape the Earth's surface. Volcanoes create new land, release gases and ash into the atmosphere and can be source of geothermal energy. Next, tectonics helps understand plate movement, mountain formation, and earthquake generation. Imagine a giant puzzle made up of massive interlocking pieces. That's a simplified picture of plate tectonics. It's the theory that explains how the Earth's outer layer, called the lithosphere, is broken into large pieces called tectonic plates. These plates are constantly moving, interacting with each other, and shaping the Earth's surface. Here's how it works: plate movement, mountain formation, and earthquake generation. Here's the quick breakdown: plate movement, mountain formation, and earthquake generation. Plate tectonics is a powerful theory that helps us understand many of the Earth's most dramatic features, from the towering Himalayas to the devastating earthquakes that can shake our planet. Next is structural geology, analyzing rock deformation to understand the history of region. So, structural geology is like reading a book written in the language of rocks. It delves into the study of rock deformation, analyzing how rocks have been bent, broken, and twisted to decipher the geological history of region. By examining the patterns of deformation, structural geologists can reconstruct the forces that have acted upon the Earth's crust over millions of years. Here's the breakdown of how structural geology unravels the past. 1. Recognizing deformation. Folds. These are bands of curves in rock layers formed by compressional forces. Faults. These are fractures in rocks where there has been movement. Joints. These are cracks in rocks that haven't moved past each other. 2. Analyzing deformation. Stress and strain. Stress is the force applied to the rock, while strain is the resulting deformation. And brittle versus ductile deformation. So, brittle deformation occurs when rocks break under stress, forming faults and fractures. And geological maps and cross sections. Structural geologists use geological maps to show the distribution of rock units and structural features. 3. Interpreting the history. Tectonic events. By analyzing the patterns of deformation, structural geologists can identify past tectonic events such as mountain building, rifting, and plate collisions. Timing of events. Dating the rocks and the deformation features helps establish the sequence of geological events. And resource exploration. Structural geology is crucial for mineral and hydrocarbon exploration. Geohazards. Structural geology helps understand geological hazards like earthquakes, landslides, and volcanic activity. In essence, structural geology is a detective story about the Earth's past. By carefully examining the clues left behind in deformed rocks, geologists can piece together the history of a region, revealing the forces that have shaped our planet over millions of years. And lastly, geophysics, studying the Earth's interior and its response to stress. Imagine trying to understand the inside of a giant, mysterious ball without being able to cut it open. That's the challenge geologists faces when studying the Earth's interior. We can't simply drill down to the core, so we rely on the indirect methods to peek inside. Here's how we learn about the Earth's interior. Seismic waves. Earthquakes generate seismic waves that travel through the Earth's interior. 2. Gravity and magnetic fields. The Earth's gravity and magnetic fields are influenced by the distribution of mass and magnetism within the Earth. And 3. Meteorites. Meteorites are fragments of asteroids and other celestial bodies that have fallen to Earth. And laboratory experiments. Geologists conduct experiments in laboratories to stimulate the conditions found deep within the Earth, such as high pressure and temperature. Here's how the Earth's interior responds to stress: lithosphere, asthenosphere, and lower mantle and core. Understanding the Earth's interior is a crucial for understanding the processes by the shape of our planet. By studying seismic waves, gravity, magnetic fields, and meteorites, and conducting laboratory experiments, geologists are constantly learning more about the hidden world beneath our feet. And next, for the part of rock deformation, strain. So, strain refers to the deformation of a rock or any part of the Earth's crust in response to stress. It's the change in shape or volume that occurs when a rock is subjected to force. Imagine the Earth's crust is a giant puzzle, and each piece is a rock. When tectonic plates collide, push or pull, they apply stress on the rock pieces, causing them to deform or strain. So strain is the change in shape or volume of a rock or any part of the Earth's crust when it's subjected to a force. Imagine the Earth's crust like a giant puzzle, and which piece is a rock. When tectonic plates push, pull, or collide, they apply stress that causes these rock pieces to deform or strain. So here is the types of strain: elastic strain and plastic strain. So elastic strain. Elastic strain, this is a temporary reversible change in shape. The rock returns to its original form once the stress is removed. Think of a rubber band, stretching and then snapping back. This type of strain in common rocks under low stress levels. So, imagine stretching a rubber band. It stretches and changes shape. But when you let go, it snaps back to its original form. That's elastic strain. It's a temporary and reversible change in shape. So I have an example here for elastic strain. So as you can see there in the picture, the force is applied. So that's why it's like the rocks can behave elastically under low stress levels, meaning they can bend or stretch a little, but they will return to their original shape once the stress is removed. Think of a spring. It compresses under pressure but springs back to its original shape when the pressure is released. And next, plastic strain. So this is a permanent and irreversible change in shape. The rock does not return to its original form even after the stress is removed. This is like bending a metal rod. It will stay bent. This type of strain is common in rocks under high stress levels. Imagine bending a metal rod. It bends and changes shape, but even after you release the pressure, it stays bent. That's plastic strain. It's a permanent and irreversible change in shape. So I have an example here. So as you can see, it is the A is slit, so it is slit direction, and B is it's like swinging, a twinning direction. Rocks can behave plastically under high stress levels. They deform permanently even after the stress is removed. Think of clay. You can mold it and then it will stay in the shape. Rocks under high stress level behave similarly, permanently changing shape. Now, this is the types of strained and rocks behavior: brittle deformation and ductile deformation. So, brittle deformation. Rocks under brittle deformation experience mainly elastic strain until they reach their breaking point, leading to fractures. This is common in the Earth's upper crust, where temperatures and pressures are relatively low. Think of a brittle glass breaking. Imagine a glass bottle. If you squeeze it gently, it might bend a little, but if you squeeze too hard, it will shatter That's brittle deformation. In brittle deformation, rocks behave elastically under low stress level, but when the stress exceeds a certain point, they break. This is like a glass bottle shattering. It can withstand some pressure, but beyond a certain point, it breaks. So brittle deformation is common in the Earth's upper crust, where temperatures and pressures are relatively low. This is why we see so many faults and fractures in the upper crust. And next, ductile deformation. Rocks under ductile deformation experience both elastic and plastic strain, allowing them to bend or flow without breaking. This is common in the Earth's deeper crust and mantle where temperatures and pressures are higher. Think of a metal wire bending. Imagine a metal wire. You can bend it without breaking it, and even if you release the pressure, it will stay bent. That's ductile deformation. In ductile deformation, rocks behave like a combination of plastic and plastic strain. They can bend and flow under stress without breaking. This is similar to how a metal wire can be bent without breaking. So ductile deformation is common in the Earth's deeper crust and mantle, where the temperatures and pressures are higher. The higher temperatures makes rocks more pliable, allowing them to flow and bend instead of breaking. This is why we see so many faults and other ductile features in the Earth's deeper layer. So these are the types of measuring strength: field observations, laboratory experiments, computer modeling, tectonics, structural geology, and geophysics. First up, field observation. Observing the deformation of rocks in outcrops and landscapes. Imagine you're hiking through a rocky landscape and you see the giant fold in the rock layers, or a massive fault cutting through the hillside. That's field observation in action. Field observation is the process of directly observing and studying the deformation of rocks in their natural settings, called outcrops. Geologists go out in the field to look at these outcrops, take measurements, and collect samples. Here's how field observation help us understand rock deformation. Outcrop mapping. Geologists map the distribution of rocks and structural features in the outcrop. Measuring structures. Geologists measures the orientation of faults, and other structures. Collecting samples. Geologists collect rock samples from outcrops. And observing landscapes. Geologists also observe the overall landscape to understand how deformation has shaped the Earth's surface. So, field observation is a crucial part of structural geology. It provides first-hand evidence of rock deformation, allowing geologists to interpret the history of region and understand the forces that have shaped it. Second, laboratory experiments. Conducting experiments on a rock samples under controlled stress conditions. Imagine you're a scientist in a lab, carefully squeezing a small rock sample in a machine to see how it reacts. That's a laboratory experiment. Laboratory experiments allow geologists to study rock deformation in a controlled environment. By subjecting rock sample to different types of stress like compression, tension, or shear, they can observe how the rocks behave and measure their response. Here's how laboratory experiments help us understand rock deformation. Controlled conditions. Laboratory experiments allow geologists to control the stress applied to the rock sample, the temperature, and the pressure. Measuring deformation. Geologists use instruments to measure the strain deformation of the rock sample as it is subjected to stress. And studying microstructure. After an experiment, geologists can examine the rock sample under a microscope to study the microscopic changes that occur during deformation. And next, simulating real-world conditions. Laboratory experiments can simulate the conditions found deep within the Earth, such as high pressure and temperature. So, laboratory experiments are essential for understanding the mechanisms of rock deformation and how rocks behave under different conditions. They provide valuable data that complements field observations and help us interpret the history of the Earth's crust. Third, computer modeling. Using computer models to simulate the deformation of rocks in different geological settings. Imagine a virtual world where you can build mountains, create earthquakes, and watch how the Earth's crust reacts. That's computer modeling in action. Computer modeling allows geologists to simulate the deformation of rocks in different geological settings. They use computer programs to create virtual models of the Earth's crust, incorporating data from the field observations, laboratory experiments, and other surfaces. Here's how computer modeling helps us understand rock deformation. Complex scenarios. Computers model can simulate complex geological scenarios such as plate collisions, mountains building, and earthquake generation. Three-dimensional visualization. Three-dimensional visualization. Computer models can visualize the deformation of rocks in 3 dimensions, allow geologists to see how structures develop and interact in different geological environments. Predictive capabilities. Computer models can be used to predict how rocks will deform in the future under different scenarios. And integration of data. Computer models can integrate data from multiple sources, such as field observations, laboratory experiments, and geophysical data. So, computer modeling is a powerful tool for understanding rock deformation. It allows geologists to explore complex geological scenarios, visualize deformation in a 3 dimensions, and make predictions about future geological events. And fourth, tectonics. Explaining the movement of tectonic plates and their impact on the Earth's surface. So imagine the Earth's surface is a giant jigsaw puzzle, and the pieces are constantly moving and bumping to each other. That's the concept of plate tectonics. So plate tectonics is the theory that Earth's outer layer, called the lithosphere, is made up of large plates that are constantly moving. These plates are like giant rafts, floating on a layer of partially molten rock called the ionosphere. The movement of these plates is driven by heat from the Earth's core. Here how the movement of tectonic plates impacts the Earth's surface. So first is plate boundaries. The edges of the Earth of these plates, called the plate boundaries, are where most of the Earth's geological activity occurs. So here is the parts of the plate boundaries: divergent boundaries, convergent boundaries, and transform boundaries. So now to earthquakes. The movement of tectonic plates can cause earthquakes, especially at plate boundaries, where the plates are grinding past each other. 3. Volcanoes. Volcanoes can form at convergent boundaries, where one plate is subducted beneath the other, or at divergent boundaries, where magma rises from the mantle. 4. Mountain building. Mountain ranges are confirmed at convergent boundaries, where plates collide and push against each other. And continental drift. Over millions of years, the movement of tectonic plates has caused continents to drift across the Earth's surface. So plate tectonics is a fundamental theory in geology explaining a wide range of geological phenomena in shaping the Earth's surface as we know it. It's a dynamic process that continues to reshape our planet today. Imagine. Oh, no. Structural geology, analyzing the deformation of rocks to understand the history of a region. Imagine you're a detective trying to solve a mystery by piecing together clues from a crime scene. That's what structural geologists do. They use the deformation of rocks to understand the history of a region. Structural geology is a study of deformation of rocks and the forces that cause them. Geologists use a variety of techniques, including field observations, laboratory experiments, and computer modeling. By analyzing the deformation of rock, structural geologists can answer questions like what forces have shaped this region? They can determine the direction and magnitude of the forces that cause the deformation. When did this deformation occur? They can use the principles of stratigraphy and regiometric dating to determine the age of the deformation. How did this deformation affect the rocks? They can study the changes in the rock's composition, texture, and structure to understand the effects of deformation. What are the implications for future geological events? They can use either understanding of past deformation to predict future geological hazards, such as earthquakes or landslides. So, structural geology is a vital field and it's a vital field that helps us understand the history of the Earth and its dynamic processes. It provides insight into the forces that have shaped our planet and the hazards that we face. Next is geophysics. Studying the Earth's interior and its response to stress. Imagine you're trying to understand the inside of a house without being able to go inside. You might listen to the sounds coming from inside or look at the house's foundation. That's what geophysicists do. They study the Earth's interior without directly digging into it. Geophysics is a study of the Earth's physical properties, including its composition, structure, and processes. Geophysicists use a variety of techniques to study in the Earth's interior, including seismic waves, gravity measurements, and magnetic field and heat flow. So, geophysics also study how the Earth's interior responds to the stress, including tectonic plate motion, earthquake prediction, and volcanic activity. Geophysics is a crucial field that helps us understand the Earth's internal structure, its dynamic processes, and its response to stress. It provides insights into the forces that shape our planet and the hazards that we face. So, factors affect. Wait. Sorry. Here is the last topic. Factors affecting the kind of deformation. So, this is the types of deformation. Rock type, temperature, confining pressure, strain rate, and presence of water. So, rock type, some rocks like granite and brittle and tend to fracture under stress. Other like limestone are ductile and tend to fall. So, rock types play a big role in how a rock deforms because a different rock have different strengths and compositions. Here's a breakdown. Brittle rocks. They think of a glass bottle. It can withstand some pressure, but beyond a certain point, it shatters. And ductile rocks. Imagine a metal wire. You can bend it without breaking it, and it will stay bent even after you release the pressure. Here's why this matters. Temperature and pressure, the depth at which a rock is found also affects its behavior. Mineral composition. Different minerals have different strengths and melting points. So, rock type, temperature, pressure, and mineral composition all play a role in determining how a rock deforms. This is why some rocks fracture and other folds, creating the diverse landscape we see on Earth. Temperature. Rocks behave more ductility at higher temperatures. This is because the heat allows atoms to move more freely. So imagine you're trying to bend a piece of chocolate. If it's cold, it will snap. But if it's warm, it will bend easily. This is because the heat makes the chocolate softer and more pliable. It's similar with rocks. Temperature plays a crucial role in how rocks deform. Here's why. Atomic movement. At a higher temperature, the atoms within a rock vibrate more rapidly and have more energy. Mineral strength. The strength of minerals decreases with increasing temperature, melting point. As temperature increases, rocks get closer to their melting point. Here's how temperature affects deformation. Brittle to ductile transitions, stressed and strained. In summary, temperature has a significant impact on how rocks deform. Higher temperatures lead to more ductile behavior, while lower temperatures favor brittle behavior. Confining pressure. So rocks under confining pressure are less likely to fracture because the surrounding pressure resists the formation of fractures. Imagine squeezing a balloon. If you squeeze it gently, it might deform a little, but if you squeeze it too hard, it will burst. Confining pressure works similarly with rocks. Confining pressure is the pressure exerted on rocks from all sides. It's like being squeezed in a vice. Here's how it affects deformation. Resisting fractures. High confining pressure makes it harder for rocks to fracture, promoting ductility. Confining pressures can also promote ductile deformation. Here's how confining pressures affects deformation. Brittle ductile transition, stress and strain. So, confining pressure plays a crucial role in how rocks deform. High confining pressure makes rocks less likely to fracture and more likely to deform ductility. This is why the Earth's deeper layer, where confining pressure is high, are characterized by folded rocks and other ductile features. Strain rate. Rocks subjected to rapid stress are more likely to fracture, while rocks subjected to slow, gradual stress are more likely to deform ductility. Imagine trying to bend a piece of metal. If you bend it slowly and gradually, it will likely bend without breaking. But if you try to bend it quickly and forcefully, it's more likely to snap. Strain rate works similarly with rocks. Strain rate is the speed at which a rock deforms. It's how quickly the rock is being stretched, compressed, or sheared. Here's how it affects deformation. Rapid strain rate. Rocks subjected to rapid strain rates, like those caused by earthquakes or impacts, are more likely to fracture. And slow strain rate. Rocks are subjected to slow, gradual strain rates, like those caused by plate tectonics over millions of years, are more likely to deform ductilely. Here's how strain rate affects deformation. Brittle ductile transition, stress and strain. So strain rate is a crucial factor in determining how rocks deform. Rapid strain rates favor brittle behavior, while slow strain rates favor ductile behavior. This explains why earthquakes cause fractures and faults, while plate tectonics, which operates over long time scales, lead to the formation of faults and other ductile features. Presence of water. Water can weaken the chemical bonds in rocks, making them more ductile. Imagine you're trying to bend a piece of dry clay. It's hard and brittle, and it's likely to crack. But if you add a little water, it becomes more pliable and easier to bend. Water has similar effect on rocks. Water can significantly impact how rocks deform. Here's why. Weakening bonds. Water molecules can weaken the chemical bond between mineral grain in rocks. Lubrication. Water acts as a lubricant, allowing minerals grain to slide past each other more easily. Hydrolysis. Water can react with some minerals like feldspar to form new minerals like clay. These new minerals are often weaker and more prone to deformation. Here's how the presence of water affects deformation: brittle to ductile, stress and strain. So water plays a critical role in a rock deformation. It can weaken chemical bonds, acts as a lubricant, and promote the deformation of weaker minerals, all of which make rocks more ductile. This is why rocks in water-rich environment often exhibit more ductile deformation than dry rocks. So, thank you, and I hope this report has provided valuable insights into the fascinating world of rock deformation. Thank you for your attention, and I trust you that you gained a deeper understanding of the complex interplay of factors that shape our planet. Sorry for the error or ungrammatical that I report, but I will try my best next time. So yeah, that's all. I hope we'll see until next time. Goodbye and thank you.